large introduction here in this audience, and he's famous for his work on volatility. And I think the talk today will combine these two topics and about pricing and options and thereafter that.
Thank you very much for the kind words and for inviting me to come back. I'm also very grateful to the previous two speakers, because after those two talks about signatures and Bermudan option pricing, I don't think I need a lot of motivation for my talk, because at some level I'm going to combine these two topics. And I would like to say that this talk is based on joint work with a number of people, including my previous PhD students, Paul Hager and Luca Pelizzari. So Eduardo has convinced everybody that memory matters. And he has also convinced everybody, like here I just have a couple of more examples. So rough volatility models. So here, just like in Eduardo's talk, memory is included in a kind of linear way. Then we have also from finance, we see sometimes self-exciting phenomenon. I mean, but also outside finance, think about earthquakes, where events trigger other events in a stochastic manner. And a particular way to model this is by so-called Hawkes process. Yes, also for social phenomenons like, as you say, crime events modeling, for medical and biological problems. Then in statistical mechanics, there are models, so-called generalized Langevin equations, which come from a quite different point of view. But again, there are certain temporal correlations surviving a scaling limit. And in many, many applications from a more applied engineering sides, magnetism batteries, for instance, you have memory basically under the name of hysteresis. So memory is very important, and memory is also very challenging, because in a nutshell, it immediately blows up the dimension of the state space you're working in. So of course, at some level, you can always say, okay, I add the whole history of the system to the current state. And this reduces memory on a kind of superficial level, because then by observing the system, I know everything that has happened before. But the problem is that no matter where I start, I immediately end up with an infinite dimensional system. And an infinite dimensional system, which of course will include a lot of redundancy. So this is a very wasteful approach. And basically, as we saw also in the previous talk, both previous talks, in fact, a lot of our methods really do rely strongly on the Markov property. So for instance, in the talk by Ahmed, if you want to be a bit more specific about, for instance, the dual martingale, the duper decomposition, then in a Markovian framework, you can actually describe this very explicitly. But in a non-Markovian situation, this kind of breaks down. And we have seen slides like this before. So basically, as Ahmed showed us, if you want to solve an optimal stopping problem, if you want to price Bermudan or American options, I mean, I will say American options, but I usually mean Bermudan options. So the difference is, for the non-specialist, the difference is a Bermudan option, you can only exercise the option at the prescribed finite set of times. In an American option, in principle, you could stop at an arbitrary continuous range of times. And basically, for numerical purposes, we kind of only consider Bermudan options, and which kind of introduces a second approximation step. Basically, you approximate the continuous time optimal stopping problem by a sequence of finer and finer discrete time optimal stopping problems. So for our purposes, it's all the same. Right. So basically, as Ahmed showed us, for the primal approach, what it boils down to, at least from a numerical point of view, is computing conditional expectations of this type. And here I'm already taking advantage of the Markov property, which allows me to say that the conditional expectation given the filtration at time t is actually can be reduced to the conditioning at this on the state variable, taking a specific value. And then the idea is, and again, this is very close to some formulas that Ahmed showed us. One very basic fundamental idea is now to use simulation methods to compute such conditional expectations by regression. So you generate samples of your underlying process x at time t plus delta and at time t, and then you solve such a least squares problem using some set of basis functions as an ansatz, for instance, polynomials, but you can do, of course, much more general. And of course, here we rely on the Markov property here, right? Because if our underlying process is not a Markov process, we can still write down formally such a representation, except that we cannot condition only at the value of xt. We would have to condition at the values of x for all times s before t. Right? So this is then a path-dependent function, like we saw in the talk of Eduardo. And that means whatever basis functions we pick, they have to be functions on path space. And of course, we would need to find a suitable kind of universal set of functions on path space in order to guarantee convergence. Right. And similarly, if you go for the dual approach, as Ahmed showed us, the martingales, in particular the dupe martingale, popping up in this dual minimization problem. In principle, this is a completely general story. The difference is, if we are, say, in a diffusion setting, then we can actually say more, because then it turns out that the optimal dupe martingale is of this form. So basically, it's an integral, a stochastic integral of some function of the underlying process at time s integrated against dw. And again, of course, if we knew the value function v, then we could in principle write this down and compute directly. But of course, the idea is we don't know the value function. We want to compute it. We don't know the option price. But then we can still make an ansatz of this form, right? So we basically have a parametric family of functions. Okay, where is here it is. We have a parametric family of functions in x, and we then minimize over this parameter theta. So very similar, this boils down from a computational point of view to a very similar problem than in the primal approach. And again, if we do not have the Markov property, we can still write by, abstract measure theory lemmas. We can still write this adapted process as a measurable function with respect to the path, like here. And then we need some universal or some natural canonical basis functions on path space to proceed in this way. And basically, Eduardo has explained to us at least one way how we can do this, namely, let's take functions of the signature of the process. I mean, linear functions of the signature of the process are actually a kind of natural suggestion, but we will see later that it actually may pay off to choose nonlinear functions of the signature instead, despite linear functions in principle being enough from a universal approximation point of view. But still. So this is the story in a nutshell. What I want to show you is that, in fact, you can use the classical methods for stochastic optimal control, which rely on the Markov property. You can actually use them for a variety of non-Markovian stochastic optimal control problems if you replace your functional approximation on the state variable x by functional approximation on the signature of x. Please. Yes. I give you one motivation, and I think Eduardo also gave a motivation which goes in the same line, namely, they are in a way the analog of Taylor expansions, local Taylor expansions in time. So I agree that, I mean, they are universal. That's one thing. Are they optimal? I think the problem is you would need to come. I mean, I think that there is a certain, how should I say, a certain tension between optimality and universality, because generally speaking, I think that it doesn't really make sense to ask whether a certain representation or a certain approximation is optimal without talking about a specific problem. And in that sense, I cannot really answer that question. I mean, I think the consensus is that they actually tend to be optimal in the sense that there is a natural grading associated with signatures. And I would say that for many problems, this grading actually, recovers, works in the sense that more important information tends to be developed in lower grades, in low degree objects, which is kind of what you want, right? But this is not a mathematically rigorous statement because of course you can construct a problem where, the level 10,000 iterated integral exactly contains what you need. But I would say these are probably unnatural problems. Thank you for this question. Yeah, please interrupt at any point. Right. So, just I mean, I am prepared to give yet another introduction to signature, but after Eduardo's introduction, I think I can be quite quick here. Just the point of view that I often like to motivate signature is from the point of view of controlled differential equations. So I have a path which, for simplicity, I assume is smooth. And I consider a ODE, a controlled ODE of this type, right? And of course, we can immediately rewrite this in this form by taking derivatives. After all, I told you that X is smooth. Now, what I want to do is I want to look at this from a numerical point of view. That is, I want to solve this kind of equations. And of course, the first thing you might do is you say, okay, on the right-hand side, I treat y as a piecewise constant object. So I freeze y on the right-hand side. So in other words, y of u is y of x plus higher order terms. I plug this into the vector field. And then I solve the corresponding equation between times s and t. And of course, the idea is that t minus s is small. And then I get the Euler scheme. I get that y of t is y of s plus v of y of s times the increment x of t minus x of s, okay, plus higher order terms. And now I can do better. I can do a second order expansion. So in this case now, the idea is on the right-hand side, I consider this kind of piecewise linear, if you like, piecewise linear in x, not in t, of course, approximation of y. I again plug it into v, but I want to be able to solve the equation, so I actually apply Taylor's theorem to approximate v in this form. And then I plug it back into the ODE or into the differential equation. And I see what comes out is again the Euler scheme as before, plus an additional term. And this additional term involves now the integral of my increment against x. So an iterated integral comes up. And this is kind of a natural second order approximation of my solution over short times. And of course, you now can go on, right? So if you want, what we discuss here is a second order Taylor expansion on path space. And if you do third order, you get third order iterated integrals and so on. You can continue. And as Eduardo noted, this is, of course, not a new story. This has been done a long time ago, for instance, in the 80s by Bergomi. And now, motivated by this, the signature is now nothing but the collection of all these iterated integrals. And it turns out that the signature has some nice algebraic properties. And in order to take advantage of the properties, we need to put it into a proper framework. And the proper framework turns out to be a tensor algebra. I mean, more precisely, what you want to do is basically the idea is, I mean, these iterated integrals, as we have seen, they behave a bit like polynomials on path space. But unlike standard polynomials, these objects are non-commutative, meaning if I reorder these indices, then the iterated integrals are not the same. And that means that when I put this into an algebraic setting, I need to consider non-commutative algebras. So basically, what I get is form a power series in 1 plus d non-commuting variables. So 1 plus d because by convention, I always include time as an additional component together with my d space components. Okay. Right. And if I do this, I get the tensor algebra as a kind of natural or one way of constructing free algebras in non-commuting variables is by tensor algebra. And, okay, all of this is familiar. All of this has also been shown in Eduardo's talk. And in particular, there are three properties that are crucial for the applications later on. The first one is the chain rule. What does it say? Well, it says that if I have two paths and I concatenate them, then the signature of the concatenated path is equal to the product of the signatures of the two original paths. The product here understood in this tensor algebra. This is the first property. And as Eduardo explained, this property is important for computation of the signature. Because what it allows you to do is you have your path, you divide time interval into many small pieces. On each of the small subintervals, you approximate the path by a linear path. For a linear path, you can actually compute the signature in closed form. And then you multiply all those signatures together to get an approximation of the signature of your original path. The second key property is the shuffle identity. What this says is, if I have two linear functionals of the signature and I apply them to the signature and multiply this, what I get is another linear function of the signature. And actually, you can write down the precise form for this linear functional. And again, it helps to think of polynomials. Because what is a polynomial? A polynomial is a linear functional on the infinite dimensional object, which is the sequence of all monomials. And of course, if you have two polynomials, that means two linear functionals on the monomial series, then their product is again a polynomial, because the product of polynomials is a polynomial, right? And it's not hard to figure out what the corresponding commutative analog of this shuffle identity would be, right? Because then certain things simplify. But otherwise, this is the so-called same story, right? I mean, I'm saying this because when I first saw this shuffle identity, I was very confused, because how can it be that a nonlinear function, like the product of two linear functions, how can it be that a nonlinear function is a linear function? But of course, the idea is, okay, if you multiply two polynomials, of course you get another polynomial, but this new polynomial is of higher degree. And the same here. This new linear functional is going to be of higher degree. And that's the price you pay for this linearization, if you like. And finally, the signature encodes the path. And technically speaking, this is why I insist of always including time, because otherwise this is not strictly speaking true. Yeah. So basically, the map taking a path, putting out the signature is invertible. I should say here that this is a theoretical statement, because actually inverting the signature is not so trivial. And in fact, I would say it's an open problem how to really do it. I mean, there are some approaches, but yeah. And yeah. And basically, what we see here is already, in a nutshell, the basis for the universal approximation property. Because what we see in this shuffle identity slide formula is that the set of linear functionals on the signature, I mean, each linear function of the signature is now a function on path space, right? And this set is actually closed under multiplication. It's also closed under addition. I mean, this is kind of obvious. And so in other words, what we have here is an algebra of functions on path space. And this algebra of functions on path space, that's what the last property tells you. It is point separating. Because if I have two different paths, their signatures have to be different, otherwise this wouldn't be invertible. And therefore, I can find a linear functional such the values disagree on the two paths. So we have a algebra of functions, actually a subalgebra of the continuous functions on path space, which is point separating. And okay, this is also not difficult to see. It will contain a constant function, and therefore we can apply the Stone-Weierstrass theorem. So by the Stone-Weierstrass theorem, what we will see is this implies that this subset linear functionals of the signature of the functions on path space is dense at least on compact sets. We will come back to this point later on. Right, I'm not going to talk, I'm kind of not want to go to the rough path frame to explain what rough paths are, except maybe to mention that at this point, once we have the signature, we basically have all the ingredients that are really needed. So it would not be hard to give a fully rigorous definition of a rough path now, actually it's here. I mean, the purpose of this slide is mostly in order to justify the continuity part of the argument I made just a minute ago. Yeah. In particular, we can do this, for instance, for Brownian motion. So X, the paths X could be samples of Brownian motion. Right. That's, I guess, what I said. So continuous functionals on path space can be approximated by linear functionals of the signature on compact subsets. And that's maybe a second observation. Since the signature encodes the path, every process becomes a Markov process if we lift it to the signature process, to its signature variant. This is now an informal statement, but yeah. Right. And now we come to the optimal stopping or optimal control, more generally problem. And here I give you a slide, a figure from a paper by Becker, Geredito, and Jensen. I like this figure a lot because it shows a very, very simple problem. Well, is it a simple problem? That's actually the question, but it shows a problem that looks very simple, but has actually quite rich structure. So the problem is simply you have fractional Brownian motion and you want to solve the optimal stopping problem for fractional Brownian motion as a function of the Hurst index h. Now for h equals 1/2, fractional Brownian motion is Brownian motion and the value of the optimal stopping problem is 0 because Brownian motion is a martingale, right? So every stopping time is optimal. Now, what happens when h is greater than 1/2? Well, then the increments of the fractional Brownian motion are positively correlated. Like in the extreme case, h equals 1, actually they are totally correlated. So then the trajectories of the fractional Brownian motion are of the form t times the end value. So, you know, if you know one increment, you know all of them. And this kind of motivates strategies, right? Because basically in this extreme case, what you would do is you wait for a tiny little bit of time. you observe the value of the fractional Brownian motion. If you went up, you just continue until the end and stop at the very end. If you went down, you stop immediately. And so basically the bottom line is if h is greater than 1/2, then it's kind of makes intuitive sense that you could construct clever stopping strategies to take into advantage of the positive correlation. If h is smaller than 1/2, the increments are negatively correlated. And I find it very hard to think about, good strategies for stopping something like this. So if you're not interested in signatures, I invite you to think about this problem. And note that actually, I have a lot of things to say about why a lot of these results are very inaccurate, but the general structure is true. And actually, you see in the negatively correlated case, the value of the optimal stopping problem is much higher than in the positive. So you can even do much better, even though, for me at least, it's very unclear how to proceed. Right. I'm not going to talk much about the problem. So basically, the challenge here is that the signature is a pathwise object. So basically, this is a tool that is designed to consider problems path by path. But now we want to solve optimal control problems which are problems that are formulated in terms of filtrations of processes, of adapted processes, of martingales. So in other words, where probability measures on path space play an important role in filtrations, that is, models of flows of information play an important role. And we struggle a little bit, or Lyons, Pelizzari struggle a little bit to how to kind of connect these very different worlds. And it turns out that a good way to connect them is by looking at stopped paths, which I think were introduced by Dupere 15 years ago, which basically says that, formally you just take the union over all paths defined on intervals from 0 to t over t. Okay, and then this is a pretty trivial observation, I guess, but still, what this means is that adapted processes can be seen as measurable functions on the space of stopped paths. So in other words, basically by this tool, we can remove stochastics from the picture and reduce this highly dynamic stochastic problem to a kind of static problem defined on this stopped path, so defined on a much larger space. And then, as I said before, Stone-Weierstrass theorem, once we have now turned, as we have the correct framework, we can apply the Stone-Weierstrass theorem as I explained before. And what it shows you is that, in fact, if you take processes or linear functions of the signature as a subset of the continuous functions on path space, this is dense with respect to uniform convergence on compacts. Okay, this is nice, but this is also not very, how should I say? The problem is, of course, the compacts. Because, for instance, you now want to apply this to stochastic optimal control problems. So you're solving optimization problems on path space. And this tells you that if you restrict yourself to a compact set of paths, you can do well by using linear function of the signature. But then what happens outside of this compact set? And of course, the fear is, or that the potential problem is that the mistake you make outside of this compact set is so severe that the performance in total is kind of destroyed. You don't converge anymore. And this is specific, this is particularly pressing in this infinite dimensional setting, because of course, in infinite dimensions, compact sets are small. I mean, you know, but in principle, the same problem already appears in the finite dimensional setting, right? I mean, you have to do something about it. And it turns out that there are actually very nice generalizations of the Stone-Weierstrass theorem that people pursued like in the 50s, 60s, 70s that I unfortunately didn't know about for a few years ago, and which allow you to kind of avoid this issue. So you get global approximation results, but you pay a price. So for instance, this one by Giles from 71, it's actually formulated in a very abstract setting. Even the metric space can be generalized. What it says is you consider a subalgebra of the bounded continuous functions, and then which is point separating and vanishes nowhere. Then it stands with respect to the strict topology. And the strict topology is the topology generated by the semi-norms, which are basically parameterized by functions vanishing at infinity. Okay, so basically you need to take care of two issues: bounded functions and what happens at infinity. I mean, what happens at infinity basically in the image space and in the domain. The good news is that, okay, first of all, if you want to work with this approach, the first thing we need to do is we need to make the signatures bounded. A priori, they have no reason to do that, to be bounded. Turns out we can do this in a very nice way, and this is due to Cheverev and Oberhauser, by using so-called tensor normalizations. So we can turn the signature into a bounded object, which nevertheless still satisfies all the nice properties of the signature we had before. And they do this because in the end, you can interpret this normalization as a scaling on the path. Right. And then using this approach, you can actually then obtain global approximation results with respect to, for instance, LP spaces. So basically, if you introduce a probability measure on path space, you can determine the behavior at infinity, and in this way obtain the result. Here is that the linear functionals on the normalized signatures are dense with respect in LP with respect to pretty arbitrary finite measures on path space. The condition here, so there is a support condition here, but this support condition is satisfied in any example that I can think of, right? So basically, main example would be the Wiener measure. The Wiener measure is, so basically, you know that Brownian motion has alpha Hölder continuous path for any alpha strictly smaller than 1/2. And basically the point here is, or the point, sorry, wrong direction. The point here is the beta I can always find, I pick my alpha strictly smaller than 1/2, then of course I can always find the beta, which is strictly between alpha and 1/2. And the Wiener measure is also concentrated on the beta Hölder paths. So this support condition is, yeah, we need it technically, but it is basically innocent. Right. And with this lemma, we can now proceed and follow the program that I outlined in the first slides. We can now solve optimal stopping problems by applying the standard methods from the Markovian world. So for instance, using the dual approach, I can now here take as my martingales, I take integrals of linear functions of the signature, or of the normalized signature, to be precise, integrate against Brownian motion. And it turns out that this is taking the infimum over all the linear functionals on signature will give me the price of will solve the optimal stopping problem. And in fact, I can also turn this into a computational and implementable algorithm, meaning that I can discretize the number of exercise states. I can numerically discretize the computation of the iterated integrals. I can truncate the signature at the finite level and use finite sample size. And in the end, taking the limit in all these approximations, I can prove that this converges to the value of the optimal stopping problem. And in fact, this turns out to be a linear program. So at least at some level, you can actually compute this efficiently. And the same is true for the Longstaff-Schwarz algorithm. So you can basically apply the standard Longstaff-Schwarz algorithm and you can prove convergence. Right. And as I kind of indicated, this is not restricted to optimal stopping, but you can use more general stochastic optimal control problems. And I know time is running out. I just want to show a few numerical examples. The first one here, the bottom line here is basically we compare against the Becker-Ceredito-Jensen paper who basically use a deep learning approach to solve the same problem. And what is kind of funny is that our lower bounds from the Longstaff-Schwarz signature algorithm tend to be quite often actually higher than the upper bounds that Becker-Ceredito-Jensen construct using the dual approach. And it took us some time to understand this because that's not possible, right? I mean, and actually they have very tight upper and lower bound. But when you think about it, the reason is because our filtration is larger. So basically by the act of discretizing in time, they throw away a bit too much information. And this was kind of, I found this very interesting because this shows that you have to be careful about interpreting, upper lower bounds. Your upper bound could be an upper bound with respect to the specific approximation you choose, but not necessarily an upper bound for the actual problem you want to solve. Right. What you see here is basically the computation of the signature, the computation of the iterated integrals, especially when the Hurst index is small, can induce lots of error. So when h is very small, you should think about it like this. The strong rate of convergence is basically h for this problem. So when h is very small, this is very difficult to compute. And finally, I don't have time anymore to really show you these results, but in the end, we tried to really compute option prices in rough volatility models, and we compare linear functions of the signature, specific class of nonlinear, neural network functions of the signature, and also the so-called signature-kernel. And in a way, the thing is, in a certain way, a nonlinear function of the signature turns out to be probably the most efficient choice, because it is true that by our results, linear functions of the signature have enough approximation power. But you know that there are two kind of orthogonal approximations you do. On the one, you encode the path, and on the other side, you also need to resolve nonlinear functions. And this need to resolve nonlinear functions can sometimes push you to a very deep degree in the signature, which you can avoid by using nonlinear functions like neural networks. And in my last slide, I want to show you basically, do we really need this? So the question here is a little bit, what if I just pretend that my problem was Markovian? And what is here is basically we try in this rough volatility model, we try to distinguish which factors, which iterated integers are really needed for the problem. What is the contribution of these factors? And you see the most important factors, like here the 2, the 2, 2, are factors which are actually functions of the underlying state variable itself. However, there are some mixed terms, 2, 1, 1, 2, 2, 1, 2, which actually matter. And these mixed terms, in a way, show you that memory matters. Coming back to one of the first statements of Eduardo, basically these mixed terms are the things that, this is where the memory of the process shows up. So the bottom line is, of course, as you would expect, the state variable itself, the value of the state variable itself is the most important term in these approximations. However, memory does matter in the sense that there are significant contributions, like here, for instance, of terms which are actually not functions of this current state. Thank you very much. No. So in the numerics, we don't use it. We tried it out. It didn't make a difference for this example. But from personal experience, I would say from personal experience for, let's say, standard regression problems, I would say there it's a bit similar. So quite often you need to introduce some kind of cutoff or some kind of normalization for the theory. And for the actual numerics, in my experience, most of the time you don't need it, but sometimes you do. So sometimes you actually do. So another advantage, I mean, basically this is you know, turning the algorithm is a robustification technique. Right. Actually, even the addition is generally speaking not a signature. So what happens is that the processes or the tensors, which are signatures, they form a group in the tensor algebra. And the good thing is, this is actually a Lie group. And the Lie algebra, I mean, the logarithm defined on this Lie group mapping you to the Lie algebra is actually explicit and it's bijective. So you can avoid this issue by simply going to the so-called log signature. In other words, by working in the Lie algebra. And this is actually the free Lie algebra generated by your basis elements. So it's actually, and then then you have all the nice algebraic properties, because then in the Lie algebra, you of course closed under addition, closed under scalar multiplication, all of this. I don't remember this comment. Yes. If P increases, you can use the Chen identity, right? So you basically the signature of your process between, let's say, 0 and T plus S is equal to the signature between 0 and T times the signature between T and T plus S. Yeah. Well, I mean, yes, 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 yes. I would say this is one of the reasons why this whole method works. Because, for instance, there are some approaches to defining signatures for higher dimensional objects, in the sense that, here we're working with paths, which means functions from R to RD. Can I change this to functions from, let's say, R2 to RD, R2 to RD? So something like images, okay? And the problem is there are certain definitions of signatures, and actually this goes back to very early works in algebraic topology. I mean, Chen, who introduced signature, was an algebraic topologist. But the problem is these definitions, the Chen identity tends not to be true, which means that if I want to compute the signature of an image, I cannot decompose it into, I cannot cut the large image into many small pieces, compute the signatures on these small pieces, and then somehow reconstruct the whole thing. And that's, I mean, from a computational point of view, a big problem. Divide and conquer, right? Sorry.